My name is Dr. G. Srinivas. I am from ECE department, B.V. Raj Institute of Technology, Narsapur. Today I am going to teach a topic in antennas and wave propagation. The topic name is microwave antennas. Mainly here in the microwave antennas, I am going to teach horn antenna and parabolic reflector antennas. So in microwave antennas, we need a very high gain and very high directive antennas. Because to transmit signal to the longer distances. So if you want to use it for some satellite application, very long distance, this high gain antennas are very much required. So today I am going to teach two types of antennas. One is horn antenna. So today my first heading is horn antennas. Horn antennas. Coming to horn antennas, they're simple in construction. That is a waveguide structure. If you take a waveguide is a hollow metallic waveguide. If you take, it will pass the microwaves. It will pass the microwaves in the hollow metallic waveguide. Okay, this hollow metallic waveguide, if the ending part of this hollow metallic waveguide is opening like this, opening like this, or it is called as flaring of the waveguide. Okay, this part is flaring. From this part, flaring will come. So from here onwards, the waveguide is flaring apart, and here the waveguide mouth and this ending part of the antenna aperture is very high compared to waveguide. So this, because of this flaring, impedance matching will occur. Impedance matching occurs, and wave will convert from guided medium into, this is a guided medium, into plane waves or electromagnetic waves. Okay, the wave is converting from guided medium to electromagnetic waves by using this flaring part. So this part is called horn antennas. This part is called horn antennas. So these antennas mainly we use to get broadband impedance matching. Broadband impedance matching, and to get high gain and directivity. They use normally in the frequency range of 300 MHz to some 330 GHz. They can be used over a wide range of frequencies. Okay. So depending on the opening, whatever the flaring is there, this flaring is different types. So different types. Depending on that, there are different types of horn antennas are there. Different types of horn antennas. First one is sectoral horn antennas. Sectoral horn antennas. In this, there are two types. One is E plane. Second one is H plane. Normally, if you check electromagnetic wave, we will take E is vertical to the earth and H is horizontal to the earth. So, if the opening, whatever the flaring part is there, if it is in the direction of E, that is E plane sectoral horn antenna. So if you take E plane sectoral horn antenna, the opening is in E plane. See here the diagram. Opening is in E plane. Here it is opening in E plane. So this one E plane sectoral horn antenna. Coming to H plane, it is opening in H plane. It is opening in H plane. See here the opening part is vertical to the earth. That's why it is E plane. Here the opening part is horizontal. Here the opening part is horizontal. That's why it is H plane sectoral horn antenna. Okay, this is the first category of antenna. And if the second category, here pyramidal horn antenna. Pyramidal horn antenna. Okay, we have seen pyramidal horn antenna. Pyramidal structures in Egypt, they are like this shape. Okay, so they are like this shape. So here opening is in only E plane, here opening is in only H plane. So if you have opening in both the planes, see the mouth part, it is completely like an pyramidal structure. If the opening is in both E plane and H plane, this is called pyramidal horn antennas. Okay, and in this category, here some exponential term will come. Exponential term will come if the flaring, whatever it is there, if it is exponentially, it is happening. If it is exponential, then it is exponentially pyramidal horn antennas. Okay, the flaring, whatever it is there, if it is exponential, that is exponentially pyramidal horn antenna. Exponential pyramidal horn antennas. Okay. The next category we have is conical horn antennas. Conical horn antennas. Conical horn antennas, normally we have taken the previous shapes. If you take, this is like a rectangle shape. This is like rectangle shape, but here the opening, and here we have taken a circular waveguide, and the opening whatever we have aperture, it is also circular. Okay, now then this type of antennas are conical horn antennas. Okay, these are some different types of horn antennas. Okay, if you check there are two types, that is sectoral horn antennas, that is E plane sectoral horn antenna and H plane sectoral horn antenna. In E plane, this is in the direction of E. In H plane, it is the opening is in the direction of H. And coming to pyramidal horn antennas, it is the opening is in both the planes. And if exponential, if term is coming now, whatever the flaring part is there, that is in the exponential manner. Next, conical means the opening part, whatever the waveguide it is there, it is in circular shape. Okay, this is about different types of antennas. Then what is the principle of horn antennas? Principle of horn antennas. Principle of horn antennas. So what is the design principle? What is the design principle it is? So for this one, we have one principle, that is Fermat principle. Fermat's principle. That the name of this one is principle of equal path length. Principle of equal path length. Okay. So by this concept, we can understand what is the design principle of horn antennas. Okay. Here just now, if you see the waveguide, either you take pyramid. Here we have taken pyramidal horn antenna only. Pyramidal. There are two types. One is E and H plane. Okay, it is applicable for both E plane and H plane separately. So either you take E plane or H plane. So the wave will travel like this in the medium, guided medium. The TV10 mode is like propagating like this. Okay. when it is reaching the flaring part. When it is reaching the flaring part, this plane wave will convert as a spherical wave, spherical manner. See here, it is converting as a spherical. It is converting as a spherical manner. Okay. So here, from here to here, the distance traveled, if you take L, the distance traveled, if you take L, and the same distance traveled here also, the same distance traveled here. This is actually mechanism of the wave which is traveling in the wave. But here the opening, whatever we are taking, opening up aperture length, we are taking like this. Okay. Here the wave is traveled up to this distance is L. But here if you check, here some extra distance is traveled. Extra distance is traveled, that is delta. Here the some extra distance is traveled coming to the wave which is traveled at the axis is L, but here at the ends the wave is traveled some extra distance, that is delta. This is path length difference. Okay, here delta is path length difference compared to the wave which you traveled at the center. Okay. So from this we can draw the diagram like this. If you take either E plane or H plane, E plane or H plane. So here the length is L, but here the length is L plus delta. And here the opening of the aperture, the length of aperture is A. And the flaring angle, here the angle is made theta. This is theta is flaring angle. Flaring angle. Okay, this is aperture length. Aperture length. Okay, this delta is path length difference. This L is length of the horn. Length of the horn. This is length of the horn. Here theta is different for E plane and H plane, and delta is also different for E plane H plane, and AE also, AE for E plane, AH for H plane, but length is common to both of them. So from this is length L. From this, here we can make a triangle here. This is the one triangle. This triangle, if we draw here, this is L plus delta. This is L. This is A by 2. And this is theta by 2. So for this, we can apply the formulas. The first one is trigonometric formulas. You can apply. First one, sin theta by 2 is equal to A by 2 by L plus delta. Next one, cos theta by 2 is equal to L by L plus delta. Then tan theta by 2 is equal to A by 2 by L. So these are the formulas we can derive from the trigonometry. Okay, these are different formulas. These are formulas will give the relationship between aperture length and the horn length and phase difference. These formulas will give the relationship between them. And one more formula we can derive from Pythagoras theorem, that is L plus delta whole square equal to A by 2 whole square plus L square. So from this, L square plus delta square plus 2L delta is equal to A square by 4 plus L square. So here delta, actually it is very small compared to L. This is very small phase difference we will take, that's why it is very small, so we can neglect this one. So then the relation will become L square, and we can get cancel this L square and L square. So what is the left out? This is 2L delta is equal to A square by 4. Then from this, delta equal to A square by 8L. This is one more important relation for the horn antenna. Okay. Otherwise, you can write L equal to A square by 8 delta. These are the one important relations for the horn antenna. See, these are very simple relationships. We have played only trigonometric formulas only. We are not going deep in this one. And from this we can get flare angle also. From this, if you take flare angle, theta equal to 2 cos inverse L by L plus delta. Okay. For each formula we can get different flare angles. Flare angle formulas. Okay. To tan inverse A by 2L. So these are the formulas. These are the formulas which are given between length of the horn and flare angle and aperture. Okay. Then coming to directivity. Before directivity, we need to discuss one optimum horn antenna. Optimum horn antenna. What is the optimum horn antenna? Actually, if you want to get plane wave from the horn antenna, your flare angle should be very small. Your flare angle should be very small. Then what happens? Your horn antenna should be very large. This is very large you have to take to get the plane wave. Okay. But for this one, size is very high. Size is very high. Here you will get good radiation with less beam width, but size is very large. So this is the drawback. Actually, nowadays we need to design very compact antennas. We don't want very large size antennas. Okay. So we need to decrease the size by taking large angle, large aperture. Large aperture by taking high flare, more flare angles. Okay, but we can design like this. But what happens with this? Beam width will be increase. Beam width is increase. So this is one more drawback. We don't want more beam width also. Okay, now while designing like this, now when this delta, whenever this delta approaches 180 degrees. When delta approaches 180 degrees, then the directive wave and this wave which is traveling at the ends of the horn, both will come in opposite. Okay, now at the axis wave is coming like this, at the ends it is coming opposite. So both will get cancelled and you will get less directivity. So this is also one more drawback. Delta the path length difference should not produce 180 degrees also. So by considering this, we don't want large size, we don't want more beam width, we don't want delta should be 180 degrees. By considering all these parameters, by taking all the parameters into consideration, and we should not get more more sage, we should not get more beam width. So we need to design optimum horn antenna by considering all these parameters. Okay, that optimum horn antenna dimensions also we can derive from these formulas. Okay, now the same formula, if you take these formulas, from these formulas only we can derive, we can get a L value and delta value for the optimum horn antenna also. But we need to take this all the parameters into consideration, that we should not get more large size, we should not get more beam width also, and we should not get delta 180 degrees also, because directivity will be decreased. Okay, now we should consider all these parameters and we should design a optimum horn antenna. Then coming to directivity or power gain or directivity formula. Directivity formula for this one is 4 pi AE by lambda square. So this is one regular formula we have. So here AE is effective aperture. Okay. See, this AE normally we will write as aperture efficiency into physical aperture. Okay. So this one, if you substitute, D is equal to 4 pi by lambda square into EAP into AP. This is physical aperture per aperture, and this is aperture efficiency. By substituting this, normally for the horn antenna, this aperture efficiency is 0.6. If you substitute these values, 4 pi, this is 0.6, then AP by lambda square, you will get 7.85 AP by lambda square. This is directivity you will get for the horn antenna. Okay, and coming to this AP, aperture efficient, physical aperture is, we can write it as aperture in E plane and aperture in H plane. So we can write this form. Okay, now if it is in terms of lambda, then we need not to consider lambda square. So D equal to, D in dB, we can write it as 10 log 10 7.5 AE lambda and AH lambda. They have taken in terms of lambda, so we need not to take lambda square. Okay, now both lambdas will. So this is actually directivity of horn antennas. Okay, and one more important relation, half power beam width in E plane is 56 degrees by AE lambda, and half power beam width in H plane, it is 67 degrees by AH lambda. So these are the some important relations we have for the horn antenna. Then coming to advantages. Advantages, normal regular advantages we can write, because they are designed to provide high gain. So beam width is less. Next, high directivity, low side lobes. Like this we can do. Coming to disadvantages. Flaring angle will decide. Flaring angle decides the directivity. So adjustment of flaring angle is difficult. Adjustment of flaring angle to get high directivity is difficult. Okay, like this we can write. Coming to applications, these antennas mainly we can use in microwave applications, very high frequency applications or microwave applications. Second one, astronomy applications. Like we can write all satellite application, weather applications, environment applications. Okay, skywave propagation, everything we can, every astronomy applications we can use this horn antennas. Okay, this is about horn antennas. Coming to next topic, we are going to discuss parabolic reflector antennas. parabolic reflector antennas. Okay, so the concept of parabola reflector is to produce a very high gain. Okay, here what happened? Parabola reflector is not a actual antenna. It is just a copper plate. Copper reflector is placed in front of antenna. So if you take any here the antenna, either it may be horn antenna, so you can keep either horn antenna or a dipole antenna, whatever it may be. You will place here, and the parabola reflector will be placed in front of the horn antenna or dipole antenna, whatever it may be. You can take here the feed antenna. It may be horn or dipole or isotropic or anything you can take. Okay, antenna may be anything. This parabola reflector will give you some different properties. By taking this parabola reflector like this, it can produce very high gain. How it will produce, we will see here. The main concept of this parabola reflector is to produce a collimated rays. See here. Actually, this horn antenna, they can produce in spherical manner. They can produce the waves in spherical manner. They will produce in dispersive manner like this. This horn antenna normally they will produce in dispersive manner like this. But when they incident on the parabola reflector, then all the rays will be reflected and they will become parallel, and they will become at the aperture they will become same phase. So in the return journey, all the rays will become, these all are dispersive from the horn antenna, and in the return journey they will become in same phase. They will become in same phase. So by this we can produce very high gain. By this we can produce very high gain with less beam width. Okay. So what is the design principle of horn antenna? What is the design principle of horn antenna? Coming to design principle, here if you take a parabola shape and here feed antenna, how much distance the wave is traveling from here to the parabola and in the return journey, how much distance it is? Total distance is L plus L 2L is equal to, if you take any ray, any one of the ray in all these things, any one of the ray in all these things, any one of ray in all these things, if it is the if it is the radius of the parabola is r, then this r plus, and how much distance it is traveling to the here. This distance is, if you normally this is the theta we will take, this is the theta we will take, then this will be theta, then the total distance traveled by this path 1 is L plus L is 2L, and this is path 2. Path 2 we will write it as r plus this distance is r cos theta. R cos theta. So we can write it as 2L equal to r into 1 plus cos theta. So from this we can write r equal to 2L by 1 plus cos theta. So this is actually the design contour of the parabola to get collimated rays. If you choose the contour in this with this formula, then we can able to produce the collimated rays. Or one more formula you can take is, if you take this is F and this point on the parabola is P. Then this is some directrix. If you take directrix, it is at a distance of Q. Okay, this here the condition should be PF equal to PQ. If you take, then all the rays will arrive at the same phase at a distance A dash. A dash. Here all the rays arrive at same phase. Okay, the distance here is S. If you take, then from this the condition should be PF plus PS is equal to PF plus PS. You can write it as QS minus PQ. So from this formula, if you substitute PF plus QS minus PF, this both will cancel. This is QS. So this is one more method, one more condition to be satisfied to get collimated rays. This is the two conditions, or any one of the condition to be satisfied by the parabola reflector to get the collimated rays. Okay, this is actually design principle of parabola reflector. Okay, then coming to parabola reflector, we need to mainly discuss about different types of feeding methods. Okay, we need to discuss about feeding methods. What are the different types of feeding methods in the parabola reflector? First one, axial feed. Whatever we have seen whatever we have seen till now, that is axial feed. Here feeding is there, rays will be emptied like this. This is axial feed. The second method is, here what happened, feeding actually placed at the focal point. So this will be aperture blocking will occur here. Aperture blocking. So to avoid this concept, we will go for Cassegrain feed. In Cassegrain feed, we will discuss this one in next page. Coming to Cassegrain feed, the feed antenna will be placed in the the feed antenna will be placed in the contour itself. Okay, and here we place a hyperbola reflector as a secondary reflector. Here it is secondary reflector. This is primary reflector. Okay, when we place the secondary reflector, then these rays will first intercept on the secondary reflector, then they will once again reflected back by the primary reflector, and they will become collimated. Like this, collimated rays will be produced. First they will incident on the secondary reflector, then they will incident once again on the primary reflector, and they will come in the same phase, that is collimated rays. So this is one type of method. Third method is Gregorian feed. Here this reflector we have taken is a concave. If you take this is convex reflector, if you take a convex reflector, this will be a Gregorian feed. Here these rays will be first incident on the second reflector, then incident on the primary reflector. Like this, collimated rays will be produced. Okay, now this is the difference between Cassegrain and Gregorian. Here we use concave, here we use convex. Okay, these are the feeding methods. And the major drawbacks in the parabola reflector is spillover and backlobe radiation. Okay, this is decided by f by d ratio. Okay, when first of all we will take f by d, f is greater than d by 4, means focal point is outside the aperture. Focal point is outside the aperture. Then what will happen? This actually, if you take any harness or anything, they will be radiate the rays and they will incident on the reflector. But when we are taking this f is outside the reflector, because of this, some rays will not be covered by the reflector. Okay, this will be called spillover. Okay, if you take f is d by 4, you will get maximum coverage and you will get maximum directivity. F is on the d by 4. If f is less than d by 4, then they are not able to produce coherent beams. They cannot produce coherent. They cannot produce collimated rays. Okay, so when d it is greater than d by 4, whatever the rays coming outside the aperture, that is called spillover. And when it is giving the good radiation, and here when you take f is less than d by 4, they cannot produce collimator. And what is back lobe radiation? Back lobe radiation means if you take the same case here, actually the rays should be incident on the reflector and they should come back. But some of the rays, they will travel in the forward direction. Okay, these forward direction rays actually these are not the mechanism of parabola reflector. Okay, but they should be reflected from the parabola and it should come in the forward direction. But these are not reflected, but they will come in the forward. They will come in the whatever the desired direction. These are called back lobe radiation. Okay, these are called back lobe radiation. Okay, coming to some important formula for this one is direct power gain is same formula. We can write 4 pi Ae by lambda square, which we have discussed for R and R antenna. This is the same formula here. Here Ae is aperture efficiency into physical aperture, and we can substitute that one, eta Ap by lambda square. And here if you take here Ap is coming as pi r square actually, but we don't have r value, we have diameter, that is d by 2 whole square. This is pi d square by 4. If you substitute this formula, if you substitute this pi d square by 4 in this formula, you will get power gain and efficiency normally for this parabolic reflector is 0.65. So okay, if you substitute this formulas, efficiency is 0.65 and this AP is pi d square by 4, you will get answer. You will get the answer 6 into d by lambda whole square. This is very, very important for the parabola reflector. Okay, and coming to half power beam width, it is 58 into lambda by d. This is also very important formula for this one. Okay, so this is about parabola reflector. This power gain formula we need to remember, and half power beam width is 58 into lambda by d. This is about parabola reflector. Coming to advantages. They can produce high directivity, low beam width, whatever we have covered for harness, same we can applicable here also. They can produce high directivity, low beam width, less side lobes also we can write side lobes. Okay, this is advantages. Coming to disadvantages. Due to feeding, whatever the feeding is we are giving, because of this some radiation will be blocked. some radiation will be blocked. Okay, so we have to remove this one. Okay, and coming to applications, they can use it in satellite applications. If you see in our homes, DTH antennas, everything will be this parabola reflector only, and we can use in same telemetry applications. Okay, application. Okay, this is about parabola reflector. Okay.
Like, share and subscribe. Hit the bell icon for more updates.